Hello, welcome. In this video, we will look at a nice problem related to moment of inertia. You can pause the video here and try the question on your own. Let me go straight into the solution now. So we are being asked about moment of inertia of the triangles about axes coincident with their respective sides. So let us draw these axes first to get an idea. So these are the two axes. This first axis, let us call the moment of inertia about this axis I1 and moment of inertia about this axis I2. So we are being asked the ratio I1 I1 by I2, and we are given that the size of these triangular plates is in the ratio 1:2. So we can solve this without actually knowing the result of the moment of inertia. The moment of inertia of an equilateral triangle about an axis which is coincident with one of its sides will have some kind of formula, but we don't really need to know the formula. If we already know the formula, then it is obviously very easy, but we can also do it without knowing that formula, and that is the interesting part. So whatever that formula is for I1, it will be the mass of the first plate times a square times some constant, let's say k1, right? So we have all studied moment of inertia, and we know that the result for moment of inertia is always in the form some constant times the mass of the body times the square of some length related to the body, right? For example, if we have a cylinder, if we have a uniform cylinder and we are finding moment of inertia about its axis, we can draw the example over here. So if we want to find moment of inertia about this, and this radius is r, then that moment of inertia is half mass times r square if this is a solid cylinder. So it's a solid cylinder. Moment of inertia is half times mr square. If we have a sphere, let's say a solid sphere, want to find moment of inertia about the diameter, the formula is 2 by 5 mr square if r is the radius, right? So you can observe a pattern over here that the moment of inertia always has the form some constant times the mass of the body times the square of some length in the body, of some kind of length in the body, right? That length I can change. So if I want to express it, for example, I'll give you an example over here, that for this sphere example, if I want to express this result in terms of the diameter of the sphere, so diameter is d is equal to 2r. So I can convert this formula, I can write 2 by 5 m times d by, I'm sorry, so r I can write d by 2 times square, right? So this result can also be expressed in terms of the diameter, but then the constant outside will change, so it will become 1 by 10 md square, but it is still in the same form. It still remains in the same basic form of a constant times the mass of the body times some length. The length can be any particular length in the body, but the constant will change, right? So the only not the only one, but the most important, the most obvious choice for a length in this triangle is the side length, and therefore the formula for the moment of inertia about a side can be expressed, will be most conveniently expressed as some constant times the mass of the body times a square. So let us highlight this, right? And this result can easily give us a clue into the ratio of the moment of inertia of these two bodies, because the mass itself of the triangular plate will be proportional to a square again, because we are being told that the plates which are in the shape of equilateral triangles have been cut out of a uniform thin sheet of metal. So if I cut out a triangle of side length A of mass, so this is side length A and mass m1, this is side length 2A, and this is mass m2, then I can be sure that the second plate will have mass which is 4 times the mass of the first plate, because the plates are being cut out of a uniform thin sheet of metal. The more area you cut out of that plate, the more mass you get, and therefore you can say that mass is proportional to the square of the side length, because the area of the plate. So you can say mass is proportional to the area of the plate, and area itself is proportional to the side length. It is, we all know the formula root 3 by 4 a square, but we only need the proportionality right now. So the mass itself is proportional to a square, and therefore we can say that I1 is proportional to a to the power 4. So the moment of inertia of this plate will be proportional to the fourth power of the side length. If you cut out, let's say, a plate of side length A compared to plate of side length 2A, the moment of inertia, if the moment of inertia here is 1 unit, the moment of inertia here will be 16 units. So that ratio will be 16 times. So this is what we have observed in this video, that moment of inertia of a planar body. So we can sort of generalize this or summarize this result, that moment of inertia of planar bodies is proportional to fourth power of some length of the body. Thank you for watching.